Morning, students. In the last lecture, you have learned various other structures, which is called threaded binary tree, which facilitates the traversal without recursion. And another one is AVL tree, which is using the rotate to balance a binary tree. So actually, I have a plan to give you a problem for implementing AVL tree, but it seems somewhat complex for you because you didn't implement it BST. So I just relieved the difficulty level. So today's problem is easy for you for implementing BST. Okay, so do you have any questions up to the which was covered in the last lecture? Any questions? No questions? Okay, then I'll switch the screen to your handout of today. So the AVL tree may be a good problem for your final exam. So I'm not sure, but it can be. So I'll switch the screen to the today's problem to make you prepare it very fast manner. So here I implemented a binary search tree. So today's problem is binary search tree for string. So you can use safely used string type of in STM. So those who are familiar to STM may use it. Okay, so string, in order to use a string, you may include string header file, or such as like this. Okay, string header file like this. Even though it is not used today for the string type, but just repeating characters to make a string, which was used in the indentation. So the binary search tree is an efficient search structure once it is balanced, okay, providing the search operation in order of log n for the best cases. So once it is balanced, so the balancing is important problem in BST. So you may apply AVL technique, AVL tree technique, which is adopting rotation, such as if you have this kind of skewed one, you may rotate this like this, so you can make it here without changing the order of, so you'd like to lift this up to the root for the using a rotation. So the AVL is using 4 types of rotations: for the left skewed one, for the right skewed one, left and right, right and left. So they are applying various cases, but beware that the cases is only 4. Okay, so that is very very cunning technique for that, smart technique for that. So the following code shows a BST storing integers. So I showed you an integer template, but you want to extend it to a string. So it is very simple, just changing the type into string. That is sufficient to solve today's problem, okay? So let me show this in full way, removing all the nodes. Maybe it is not fully covered in a single screen, okay? But the BST implementation is still usable. So in the last binary tree implementation, you are using 2 types of things: node, tree nodes, node type, and tree type. And you are using the node type from the tree type. So in that way, you are making a node and tree separately. But for today's problem, you are using BST. It's a single file, a single class. So the data and left subtree and right subtree is all fully implemented here. But I assuming that the root of BST is available as a static member. So it is assumed that the BST has only one instance. So using BST constructor do nothing. Okay, it does not allocate anything. But once you'd like to make a BST using a data, it is actually creating a node with left and right subtrees unknown. And insert D is actually calling another insert operation and passing the root and the data. So the another insert operation is currently using the root. Examine the node, current node. If it is null, then you are making a new BST using this constructor and returning it. And the returned value is set as root. Okay. If it is not, then it is compared. The current data is compared to the root data. Okay. So it is greater than, it is inserted to the right. If it is less than or equal, it is inserted to the left. And the returned tree is set as the right tree or set as the left tree, because the left tree may be empty or making a new node. So it is set as right tree, right subtree, and left subtree as a returned value, because this is also used for the leaf cases. Return and the final tree is returned. And for print mechanism is similar to insert. The print, the standard interface for print is using the out as a default argument, the cout. So your root is used for print with indent 0. And the indentation level is incremented by 4 for each recursive call. And I use the string constructor here to repeat the indentation level with spaces. So it is much like that in Python. You are using that a string is multiplied by depth. So this can be implemented in string constructor, but yeah, this is only a character, not a string. So you are constructing an indent, and the indent is actually printed for the current data. But beware that it is printed as in order manner, because you have to tell the difference left one and right one. So left subtree is printed first, and your root, current root is printed, and right subtree is printed next. Okay. So actually this print is not called from the outside. You may lift this up. You may move this up as a private or protected. It is also okay. Private or protected. It is also good for your encapsulation. And your current root static member should be initialized outside of the class declaration. So it is set as here with the scope resolution operator. So actually it is a scope resolution operator here. Okay. And the type of the root is BST pointer as described here. So you have to read this as it is setting the type of BST pointer root who is in the scope of the class BST, and it is set as null pointer. Do you have any questions up to here? No questions? Okay. And the main function is very simple. You are making a new BST as a tree. So since it is an empty BST, do nothing, but you know that the root is currently none. So you want to insert the elements, these elements from the BST. So you may assume that, so this is a very convenient for every member in NS, you want to insert it and you'd like to print the tree, okay? So inserting 4 will make 4 as a root. Since the root is 4, so you are using this one, okay, this one, and new BST is constructed as 4. And both of the children are none, set as none. And you'd like to insert 1, you're comparing 4 and 1. Since it is less than to the current data, it is inserted to the left subtree, and you found that left subtree is none. So it is set, new node is created, and it is returned. And it is set as a left subtree. And for inserting 2, comparing this less than, comparing this greater than, so it is inserted here. For 3, less than, greater than, so it is inserted here. For 6, it is greater than, so it is inserted as 6 here. For 5, comparing this greater than, comparing this less than, so it is inserted as here. 7, comparing this greater than, comparing this greater than 6, so it is inserted into here. So your tree should be shaped like this, okay? So you can find that this is left skewed because, right skewed because the inserted order is not maintaining, is not maintained in your normal binary search tree. Okay, so in AVL tree, once you are inserting 3, you are comparing that the balancing factor, and the balancing factor is 2, so it is rotated. It is not needed for today, but I'm just explaining that for the case of AVL tree, you want to lift this up and you want to make this as a subtree of 2. So once it is balanced, this part, this right subtree, left subtree will be made as 2, 1, and 3. And this is not changed, okay? And you know that if it has some tree here, it is maintained here, okay? Since it is skewed, there's no right, left one here. So in AVL manner, it should be rotated, but in this plain implementation, it is not balanced. Do you have any questions up here? No questions? Okay, then I'll switch the screen to your Visual Studio Code. I have to reshare Visual Studio Code. So this is simply an implementation of the same code here. So you can just take a look. It is literally same because I copied these contents and paste it to your handout. So you can just execute this and just enlarging this a little bit, okay? Since for the tree was written in previous slide, previous handout, I wrote this 4, 1, 2, 3, 6, 5, 7, okay? So remember that the left subtree is skewed. So it is skewed like this. So you know that this is the left subtree. And you know that this is the right subtree. So this is a root, okay? So you have some idea that if it is inserted in different order or in here, then you can make a balanced tree. So rather than inserting 1 first, you may insert 2 first, then you can make a balanced tree, okay? So let's try that. Deleting everything, and in this one, you are inserting 2 first, and 3, 1 maybe interchange it in any way, okay? So if you make the insertion order in a different order, you may execute this. And you know that it is fully balanced, okay? So if you insert the elements in a pre-order manner, then the resulting tree will be balanced, okay? So as another trial, I said that this insertion may be moved into private. So let's make this as a private. This one may be moved into a private member. So let's use an empty line to separate this with members. And how about this? This may be moved into the private member. Okay. So your public is somewhat simplified. Okay. Save this and running this again. Same way. It is executed in the same way. Okay. So do you have any questions with this code? No questions? Okay. Then I'll explain today's problem, the switching to the current handout. Note the way the printing tree is much like an the showing the left and the right subtree is explicit. So the order is important. So if you'd like to make it as okay, so you may try this again. If it is not printed as an in order manner, you may want to print this here first, so pre-order manner. Then the trees may be cannot be identified correctly. Okay, so if you print this, this is good. This is good for balanced one, but once you'd like to determine that 1, 2, 3, 4, 5, 6, 7, okay, then you don't know which this is a left one or a right one. You don't know that you cannot tell the difference. So that's why I printed this as an in order manner. So if you print this as an in order manner, saving this, and you know that at this time, this is all of these is the right subtrace. Okay, not the left one. So it seems the output is decipherable once you make printed as an in order manner. So that's why I used an in order manner here. Also note that BSD is maintaining a static member root, implying that there exists only one BSD instance in the whole program. And string BSD. So write a program implementing a binary search tree for string keys. Your program should also support a method for returning keys at depth k in the current tree. For example, you can use a vector of a string in STL for returning the string. The depth of root is 1, and the depth of a child of a node of depth k is k plus 1. So let me just make it explicit with a simple example. So since if you have this kind of tree, 4, 5, 6, 1, this is depth of 1. This has a depth of 2. Since the parent is depth of 1, it is 1 plus the depth of the parent, 2. This is depth of 3, okay? So given a sequence of string, if your sequence of string hello data structures in C, so actually I want to use this as C++, but I want them as the alphanumeric strings, so I just use the C, okay? So hello, you are inserting hello as a single root. Hello is the root. And both of the left and right is null. So this is much like a tree structure. You may decipher this. And data is less than hello because it comes first in your dictionary. So in a lexicographic order, it is less than hello. So it should be inserted here, data. So the data is inserted as a left subtree. Structures, it is greater than hello in lexicography order. So structures should be the right subtree. So it is inserted as right subtree here. In is greater, in HI, greater than hello. It is less than structure. In lexicographic order, in is inserted here. C is less than hello, less than data. So C is inserted here. So you know that this is your final structure, okay, tree structure. And you want to, the depth of 2, you know that this is the depth of 1. Depth of 2 is data structures. So your BST has a level 2. Level 2 data should be collected as data structures. So therefore, your program should print the following k, if k is 2 data structures. What if k is 3? You have to print C in. What if the k is 1? You have to print hello. Note that the keys should be printed in an increasing order because it is collected from your data, from your BST. If k is negative or 0, your program should print the root, okay? So hello should be printed if it is less than or equal to 1. If k is greater than the maximum depth, you know that the maximum depth is 3, but you want to print them, you want to print the 4, then C in should be printed, all the leaves should be printed in an increasing order. So your program should read from the standard input. The input consists of, so do you have any questions up to here? No questions? Okay. So your program is read from your standard input. The input consists of 3 lines. The first line of the input contains a positive integer n, the number of input strings, The second line contains n strings separated by a space. Each string consists of small letters only. And the last line contains an integer k, which is a depth. Your program should print the keys of the nodes at level k, I mean the depth k. Depth k to standard output. The string should be printed in an increasing lexicographic order. Print the key of the root if k is less than or equal to 1. Print the keys of the leaves if k is greater than the maximum depth. So this is the same example explained before. And how about this? Alice is the root. In should be inserted to the right subtree. Wonderland should be inserted as a right subtree. With is less than Wonderland. And an, L is less than n, so it is greater than Alice. And, R should be the greater than Alice, greater than in, less than Wonderland, less than, so R should be inserted here. For and is greater than Alice, less than in, so here and is inserted here. And Q is greater than Alice, greater than in, less than wonder, less than with, or PQR less than R. Okay, so Q should be inserted here. And you know that the depth of a root is 1, depth of in is 2, depth of and, wonder, is 3, depth of with is 4, depth of R is 5, depth of Q is 6, but K is inserted, which is greater than the maximum depth. Okay, so you have to print all the leaves. This is the leaf, this is the leaf in an increasing order. Okay. Do you have any questions? No questions? Okay, then you are going to have about 48 minutes to go. Question? So Sumin, I asked you before, but okay, please one more time explain left to right element. No, it is not length of the string. It is a lexicographic order, Sumin. So that means it is alphabetic order. Any other questions? So that's why I used restricted the input string as small letters only. So with including large letters, the lexicographic order is different to the ASCII order. You know that the capital letters comes first in the alphabet, in the ASCII order, but the lexicographic order is different for small letters. Which means that it is not applied for today's problem, but if you make this as large n, and it is less than Alice in ASCII order. As you know, the ASCII A is less than small a. But in lexicographic order, they should be same. A and small a should be same order. Any other questions? It is exactly determines the first string to be inserted. Students, I forgot to explaining the bonus point. So if you have time, so please take a look of how to obtain the bonus points today. So I will show you, I share this screen to your NeoSPAM. So the title of today's problem is not BTS, it should be BST, but maybe your TA is a fan of BTS. Anyway, so for the case of heap, so I downloaded a case of your code. So once you submit your code, so I'll explain this as the context of the last laboratory work. So if you want to submit your file, so in your code, heap, you're selecting a heap and upload it. So once you have 100 points of the code, then this is enabled, detecting code quality. So just click this. It will show you another screen for checking your code quality. So you know that there is some quality issues, 1, 2, 3, 4, 5, 6, 7, 7 quality issues here. So if you want to take a look, what is the actual issue, just click this. So max heap to match the expression. So it is for naming problem. So it is a naming problem. So the name should start with capital letters. Okay, so press this dot dot dot. It will show you the detailed explanations. Okay, the detailed explanation. So it seems good. With my method, so it should be changed to my method here. So it is almost naming problem. So how about the second case? Heap has a constructor with one argument that is not explicit. So if it is one argument, you want to make it explicit. So this is not show the full issue, but you know that the explicit means it is for use, not for a type conversion. So in order to do that, you want to make it explicit. So this is the second issue. And third issue, another naming problem. Fourth issue, another naming problem. Fifth issue is at most one statement, so you have to separate line for return. Sixth issue, another naming problem. This is another naming problem. So just changing the naming problem will give you the qualified except two symbols. So I'll switch the screen to here. to your Visual Studio Code. To make the issues, to correct the issues, max heap, the first issue. And what was the second one? I have to name max heap and explicit. And third issue is naming problem, heap add. Heap add. Add. And remove. Remove. Top value is empty. Okay, so remove. So how about use this? Top value is empty. Then you have to remove, change the code. Add is empty. Top value remove. Okay, and all the naming problems is deleted. And one issue is that for the if statement, what was that? Remove. In the remove, the if statement should have the return statement should be as. And there's another issue, you know, that this is not a quality issue, but I prefer to a single space after the keyword if and while. Okay, so please use a single space after the keyword of the control structures. So it seems good. Still has some, okay. If, for. So why should I use a single space here? Because you have to use them as you should tell the difference that it is different to your function call. Okay, so using single space make the difference. So it is also good for the class definition, okay, and method definition. Sorry, I deleted. So please use a single space here, okay. So how about this single space? Okay, too many cases. Main, okay, here and here. Okay, so this is a good habit to make it explicit for the condition. Erin, do you have any questions? I'm doing wrong. It seems a beep as a warning. Okay. I just make it down for the Erin's microphone. Okay, so she's not here, maybe. And making explicit, what was it? Heap. So this is a constructor. So you making it explicit heap, explicit constructor. So saving this, and let's submit this again. Max heap. Where? Here. Okay. 930. Max heap. Okay. Yes. So your TA is helping me. Okay, good. It seems good. So let me just resubmit this. So I'll switch the screen again to your NeoSPAM and select keep the CPP, upload. And then you can find that you are having 100 points and detecting code quality. Perfect. Okay, and then it is good. So there's no issues here. So once you get a perfect result, that may be your bonus point. But 1 or 2 issues is good. Okay, it is acceptable. So please try to have get a bonus point once you get 100 point. Okay. So do you have any questions on the problem or the data structures? No questions? Then let's call this